Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Computational Gas Dynamics, and in this list of lectures, this is the second lecture of first week, and this second lecture consists of two parts, and these two parts contains the broad topic of speed of sound and Mach number. In our previous lecture, we emphasized the fact that gas dynamics is the subject in which we study the science behind the flying object that travels at speed higher than sound. So, it is the customary that we should know what is the speed of sound, and since there are two speeds involved, one is the speed of the object or body and the speed of sound. So, a non-dimensional parameter which is introduced, that is called as Mach number, and Mach number is most important criteria or non-dimensional number that defines the compressibility effect into a systems that travels into the flow field where the where the compressibility effect becomes dominance. So, in this segment we will talk about some of the fundamental theory of wave propagations, because sound we say it is a wave, how it propagates, and mainly to know that the science behind this motion of the sound, and we need to consider in a simplest case, that is one dimensional medium. Now, once we know the sound waves, then we will try to frame the theory behind the sound waves. Now, to do that, we need to understand the one dimensional flow equations. So, in our last segment, we talked about three fundamental equations along with the perfect gas equation, that is continuity equation, momentum equation and energy equations. Then we will try to see how those equations can be framed in a one dimensional systems, and how those equations can be used to derive the speed of speed of sound and theory behind the sound waves. Then Mach number will be introduced. Additionally, there are some situations where another parameter that pops in, that is characteristics Mach number. This is again another fundamental science behind this compressible flow analysis. And in fact, when you deal with the computational aspects of gas dynamics, then we will find that apart from Mach number, characteristics Mach number is also an important significant parameter which is mainly used for computational study, because in some situations the role of Mach number becomes irrelevant, and so we introduce the term characteristics Mach number. So, although Mach number and characteristics Mach number bear same informations, but the characteristics Mach number takes the advantage as a computational tool as a non-dimensional parameter. Now, once you know this Mach number and characteristics Mach number, then we are able to define the different flow regimes that normally occurs in a compressible flow domain. So, let me start the first part, that is wave propagation in a one dimensional mediums. To define this particular concept, so I consider a system in which we have a infinite cylinder, and this cylinder contains some gas, and this gas is enclosed in these things in a cylinder, and in one side we have a piston, and but the other side there is no free bound, that means this gas is constrained by two lines, horizontal lines associated with this piston, but its length is infinite, but there is no end plate. That means, when this gas is stationary, it can be thought of, we can think of, since, and this is a constant area duct, we can imagine to be constant area duct. So, these gases can be assumed to be different layers. So, you have a cylinder, then you have piston. So, initial state, it is a stationary gas. So, the gas can be thought of having infinite number of layers. Now, what you do in the first instance, you give a push to the piston. Now, when you give a very light push, push means like that means we are just trying to give a very small velocity to these pistons. So, the movement of pistons will be sensed by the first layer of the gas, and once it is sensed, the molecules transfer this information to the next layer, and these information then carries forward to the subsequent layers. So, essentially speaking, the initial push of these pistons creates an moving wave, and that moving wave enters, travels in that piston, infinitely long pistons. Now, if you look at the moving wave point of view, what you see, the both side of the moving wave, and one side we have the stagnant gas, and this stagnant gas is nothing but at its initial stage, but this and which means that information of the piston push is not sensed by the stagnant gas, because the moving wave has not arrived. Now, the other side of that means flow, this is called as the flow ahead of the wave. This is the flow ahead of the wave, and this is the flow behind the wave. So, which means this gas inside this behind this moving wave also follows this moving wave path. So, so at a particular instant of time, we see a moving wave which is induced by the initial push of the pistons, and this moving wave induces the gas at some velocity which is lesser than this moving wave velocity, but so that means gas behind these things gets the information about this moving wave, but the gas ahead of the moving wave, which is essentially the stagnant. So, this pressure pulse is viewed as a very small wave, or this pressure pulse is viewed as a very small intensity, and it is known to be a sound waves, and this pressure pulse is also called as a compression waves, and then this is, since it is a compression waves, and this wave is moving at a velocity that is called as speed of sound. So, what I am trying to say, the weakest possible disturbance created by the small push of piston is known to be the sound waves. In fact, these sound waves can be generated in a medium. In this case, we consider this as a gas. So, this medium can be a solid, this medium can also be a liquid. So, medium may be different, but definitely given a piston, it creates a wave. So, under typical conditions the speed of sound in air is about 340 meter per second, that we will see, and the speed of sound in water is about 1450 meter per second, which means the disturbance travels faster in a water medium. So, having said this, we will try to give some kind of physical meaning in terms of data interpretations. So, what you see is that what I have explained is that there are two types of analysis we are looking at. One is moving gas analysis, other is the stationary gas analysis. Now, while looking at this moving analysis, we are sitting in a laboratory frame when you are doing a moving gas analysis, we are sitting on the sound waves and try to see what happens ahead of this wave and what happens before the wave. So, what we see, the initial state, that means small displacement of piston dV induces a wave that moves with speed of sound A in a stagnant gas which has initial pressure P and density rho, and because of this motion of and through because of these regions, the gas behind this moves at some velocity dV, and because of this region we have density changes rho plus d rho and pressure changes P plus dP. So, and if you plot them in xt diagram, that is displacement time diagram, we see that the piston moves at some path, that is piston path of pressure waves, that is sound wave that moves in these directions. And if you look at along this moving for this sound wave, if you look at the pressure difference that you see, one side it is P plus dP, other side it is only P. And in terms of velocity, the gas ahead of this wave is almost 0 velocity. So, it is there is no velocity, but before this we have velocity dV. So, this is how we view this information, the motion of the pistons. Now, what you try to do, so this is what we call as a moving gas analysis in the frame of moving gas, which means we are sitting on the sound wave and view the systems. Now, another synchronization can be done in terms of stationary gas analysis, like you keep this gas, keep this wave stationary and try to allow the flow to pass across this wave. So, this is something like the description of either Lagrangian or Eulerian descriptions. So, what you see, small piston things, it will induce a gas which and if you say it is a stationary gas which is a sound wave, it is a stationary wave, then one side we have pressure P plus dP, other side it is the pressure has P and it is a stagnant gas, and it is and then density also rho, and but if you talk in terms of velocity, one side we have velocity A because this gas has already created a velocity of sound in the medium. So, and the relative velocity is getting felt in the other sides. So, in this case we say it is before and it is after. So, this analysis is done in terms of stationary gas analysis. Now, similarly for this case, the piston path can be drawn, pressure and pressure versus X diagram can be done, because we are not looking at because we are looking at the same information here as well. So, here also you have P plus dP and here it is P and difference is dP. And but in terms of velocity, since we say it is a stationary wave, so difference in the velocity that is felt in terms of relative velocity on both sides. So, one side you say it is the velocity is minus A minus dB, other side it is A. So, likewise we normally do analysis of wave propagation in one dimensional mediums, and in our subsequent framework of analysis we will stick to the stationary gas analysis. That means, keeping the wave stationary and try to analyze the flow, what happens before the wave and what happens after the wave. So, this is the benchmark or steady analysis for all subsequent systems. Then moving further, let us now revisit the fundamental equations and try to frame the one dimensional flow equations. So, what we are looking at here is that we require, we see there is some we consider some arbitrary region in the space, and this is the arbitrary regions, and try to analyze the flow field which is passing through this region. And to do that, we create a rectangular control volume, which means it is a kind of a imaginary control volume with rectangular cross sections, as if the inlet condition is given by state 1 and the exit condition of this control volume is state 2. The flow parameters, that means when the flow parameter that enters into the control volume is defined by its flow velocity u, pressure P 1, temperature T 1, density rho 1 and internal energy E 1. So, these are the initial conditions. Now, after the flow gets out of this rectangular control volume, the property changes, that means velocity becomes u 2, pressure becomes P 2, temperature becomes T 2, density becomes rho 2. And for the simplicity of assumptions, we say it is a constant area and that is A. Now, additionally, we also assume that the fluid that is entering, it is a gas and mostly we look for air. So, and what we will see look for here, it is a steady flow, which means all time derivatives of governing equations can be assigned as 0. The momentum equations neglects body forces, viscous stresses, and energy equation does not include work done due to viscous stresses, shaft work, heat transfer, that means due to thermal conduction and diffusion. Also changes in the potential energy is also neglected, but kinetic energy change is happening because u 1 becomes u 2. So, now we revisit the basic integral form of flow equations for a steady flow analysis for the control volume. So, the continuity equations which is defined for steady flow, and by neglecting this time derivative term, so and if you evaluate that integral in terms of 1D framework, it becomes a simple expressions, that is rho 1 u 1 is equal to rho 2 u 2, and these informations are known at the inlet at the exit. That means, if you know the inlet condition, other exit conditions also can be obtained. Now, coming back to the momentum equations, here also we neglect the time derivatives due to steady flow, and we also neglect body forces, there is no body forces. So, this integral becomes for 1D regions becomes P 1 plus rho 1 u 1 square is equal to P 2 plus rho 2 u 2 square, and this is a steady flow, one dimensional without presence of body forces. Now, again for energy equations, we do not talk about this time derivative, then we do not take this shaft work. Okay. So, right hand side becomes only in this form rho e plus b 1 square by 2, that is here, and left hand side is represented in terms of by neglecting, we are actually neglecting the body forces and work done due to the body forces. So, this particular term also can be neglected. Ultimately, the simplified expressions for a systems which involves heat transfer becomes q dot by rho 1 u 1 a 1 plus u 1 plus P 1 by rho 1 plus u 1 square by 2 is equal to u 2 plus P 2 by rho 2 plus u 2 square by 2. So, here also we say that if it is adiabatic flow, this q also becomes 0. So, what the final result, important result that we get, the information that energy equation takes the form is equal to h 1 plus u 1 square by 2 is equal to h 2 plus u 2 square by 2, where heat flow per unit mass is neglected for an adiabatic system. Now, having said this, let us try to understand what happens these flow equations, these one dimensional equations, when you look for a wave front which is nothing but a sound waves. So, what you see here the figure, that instead of talking about the initial state at u1 and u2, that means velocities defined as state 1 and 2 as u1 and u2, we are saying that as if it is a sound wave front, and before this the velocities is a, and after this wave the velocity is a plus dA. Likewise, there is a slight increment in pressure P plus dP, increment is density rho plus d rho, and temperature T plus dt. So, we are now main objective, we have to find out what is this value of A, how do you evaluate this A by studying these fundamental equations, that is continuity, momentum and energy equation. How these equations gets fitted when we say it's when you define this wave as to be sound waves. So, we start with this continuity equations, that is initial state, state 1 and state 2. So, by putting this continuity equation u1 and u2, we get with information A and A plus dA, we can rewrite the equations. So, we can neglect the product of differential which involves d rho and dA. So, ultimately after simplifications, we get a information A is equal to rho times dP by d rho. Then momentum equations again can also be simplified, that is this is dP. The momentum equations can be simplified as dA is equal to dP plus a square by a square d rho by divided by minus 2a rho. So, here what we are doing, basic equation, we start with P1 plus rho 1 u1 square, put the information of P in one side, P plus dP in the other side, and u as A and u2 as a plus dA whole square. So, neglect the product of differential and simplify, we get one information dA, and subsequently further simplification we arrive at this expression A square is equal to dP by d rho. And when you look at this expression is a differential equation. But however, in real point of view, we have to give a thermodynamic meaning of these things, that when we see based on our assumption what we have done, that such a equation is possible if the medium is treated to be isentropic. So, that is what the differential equation becomes a partial, ordinary differential equation becomes partial differential equations with an assumption that process is isentropic. So, A square is now becomes dou P by dou R at constant S. Now, if you recall the basic definition of compressibility, which is tau S, and that is isothermal compressibility, which I will talk about in next class. So, here this compressibility is defined by 1 by rho d rho by dP at constant S. Now, putting this information of speed of sound here, we get an isentropic relations between speed of sound A and isothermal compressibility. So, this basic information that I am trying to involve here, that compressibility parameter gets induced through into the medium through this speed of sound and density. So, this is one important aspect of this theory behind the sound waves, and subsequently this basic definition S square is equal to dou P by dou rho at constant S, and if it is for a if you can assume it for a calorically perfect gas equations, so you can say P by rho to the power gamma is equal to constant. So, that way that way we can write A is equal to gamma P by rho. So, A is equal to gamma P by rho. So, this is the basic expressions between pressure and density relation. Of course, still still we say that pressure density relations also holds good for liquids as well. So, or solid as well. So, for that till that point of time we have not assumed the medium to be gas. So, the basic expression that speed of sound bears that A, when you say A is equal to gamma p square root of gamma p by rho. So, here one thing I can say that speed of sound is now related to the pressure in the medium and density of the mediums. Now, again if you say perfect gas equations, so here P bears the relation P is equal to rho R T. So, that particular equation P by rho becomes R T. So, A becomes square root of gamma R T. So, this is one basic information. We start speed of sound represented in partial differential equation form, now is represented as a simple form A is equal to square root of gamma R T. Now, if you revisit some theory of kinetic theory of gases which you look at, so you can say the average molecular speed is expressed as a square root of 8 R T by pi. So, from this information one can say that if you try to correlate with average molecular speed, A by molecular speed becomes 0.75, which means speed of sound is almost 75% higher than the average molecular speed. So, it is which is a quite significant number. Another important information that I can share is that with this information of speed of sound, and if you say that define the speed of object is v, we can define a non-dimensional parameter that is called Mach number, that is v by a. So, for we can define it for subsonic flow which is less than 1, we can define it for sonic flow which is equal to 1, and we can define it for supersonic flow which is greater than 1. So, here I try to give whatever I explained, what is the inferences that we get from the theory of sound waves. The speed of sound wave is a direct measure of compressibility of the gas defined through a parameter that is called isentropic compressibility. Second, speed of sound is 0.75 times the average molecular velocity estimated from the kinetic theory of gas. Another information that we can say, for instance, if you take the ratio of kinetic energy to the internal energy, one can find out that is v square by 2 divided by E, that means share of kinetic energy with internal energy at a given arbitrary situation. It can be related. So, this particular parameter can be related to the Mach number. So, as the Mach number becomes higher and higher, dominance of kinetic energy is higher. So, that means role of kinetic energy or speed of the body takes a significant becomes a significant parameter. So, through this we can find out the Mach number is m square becomes 3.5 times higher than this ratio. So, already I have talked about isentropic compressibility and average molecular speed. So, these are the some of the important inferences. Then moving further, after defining the characteristics Mach number, we are now going to define another parameter which is called characteristics Mach number. To define this characteristics Mach number, we find that in some instances, if you look at the streamlines drawn in a particular flow field. So, in this case we look a fluid element moving along a streamline with a velocity equal to flow velocity at that point. So, look at a point A where the fluid element has a velocity v and Mach number m. Now, what happens? You imagine that the fluid element changes its state from A to B, and when we say this changes its state, we imagine that the change is happened, either you slow it down, when you slow it down Mach number reduces, when or you accelerate it to Mach 1. So, what I am trying to say, at point B we say the stage it has a Mach number of 1, So, to bring this Mach number of 1, whatever velocity at state 1, either you increase or decrease, so that at point B its Mach number 1, and imagine that entire process happens in an isentropic manner. So, for that reasons, when you say it is Mach number of 1, so this particular situation we call this as the star conditions. So, that is called as characteristic state. So, when you have when it has achieved Mach number 1, obviously the pressure, temperature, everything will change. So, at that point we say temperature is defined as a T star. So, we can now define another situations, that is speed of sound at hypothetical state Mach 1 becomes A star. At that point your speed of sound become A star, and that A star can be written as square root of gamma r T star, because at that time, at that point the temperature is T star. So, if you have A star here, then we can correlate the information of point B with respect to point A by a parameter which is called as characteristics Mach number, m star is equal to V by A star. So, whereas you for an any arbitrary state, Mach number is defined as V by A. So, moving in this framework, we can now revisit the one dimensional energy equations to have some information that how this characteristics Mach number becomes relevant in the energy equations. So, we start with the energy equation, which is H1 plus U1 square by 2 is equal to H2 plus U2 square by 2, which is for an adiabatic situations. Putting enthalpy as Cp times T, Cp as gamma r by gamma minus 1 for a calorically perfect gas. These equations can now be reframed by putting the information of enthalpy and Cp, and subsequently we assume in this framework your initial state is U1 and U2 states becomes a star conditions. So, ultimately when if you set, that means at this stage we have we define the parameter A star. So, putting this equation here, we find an expression of any arbitrary state, it is involving A and U, to a relation with respect to star conditions. So, this relation becomes very vital for analysis viewpoint in the energy equation in our subsequent situations. So, another in terms this is what we do it for when you talk about when you use these equations, that is gamma r T1 by gamma minus 1 plus U1 square by 2 is equal to gamma r T2 by gamma minus 1 U2 square by 2. But however, if you put in this equation, when you put RT1 is equal to P by rho 1, we can also frame another equations that involves pressure and density. So, that way the relevance of Mach number and characteristics Mach number becomes important. So, now we are going to part 2 of this lecture, which involves the speed of sound and Mach number. So, till this point of time we have covered the first 4 segments, that is wave propagations in a one dimensional medium, one dimensional flow equations, theory of sound waves, Mach number and characteristics Mach number. Now, with these informations we are now going to classify the flow regimes in a compressible domain. So, to classify the flow regime in a compression domain, let us try to understand the basic difference between incompressible flow and compressible flow. As a fundamental understanding, we say that incompressible flows are characterized as the flows in which the density is presumed to be constant throughout. So, for all liquids and gases, for all the liquids are incompressible, flow of gases under certain conditions, the density changes are so small that assumption of constant density can be made with reasonable accuracy. So, this is what happens in an incompressible flow. Now, when you enter into the compressible domain, which means we say that effect of compressibility becomes a dominance factor. So, at what condition it becomes dominant? So, to find that, what we define this compressible flow as the variable density flow, where the density changes are considered to be 5% or higher. So, when beginning of compressible flow starts with 5%, and subsequently as and when your density change becomes more and more significant, different flow regimes can be classified. To illustrate different flow regime in the compressible domain, we consider a situation of aerodynamic body either allowing a flow to pass over it. Now, if you refer to this figure, what we have shown is here as a airfoil, which is placed in a domain in which the flow is coming and hitting onto this airflow. So, in the first case, when you say this particular side, we call this as a free stream, and this free stream flow is flowing over an aerodynamic body, and in this case it is an airfoil. That means an airfoil is placed in a flow domain, and the flow is the flow velocity or Mach number is less than 0.8. So, essentially it is characterized as a subsonic flow. Since it is a subsonic flow, the presence of body is felt. Entire information or sound wave which is generated by this presence of the body is transmitted to the entire region of the flow. That means, the streamlines which enters or passes over this aerodynamic body, and in this case airfoil, adjusts itself so that we can draw streamlines over it. So, such a flow is characterized as compressible flow. Now, what you do? You increase this Mach number, and which is falls in the region of 0.8 to 1. So, if you increase this flow velocity or Mach number, what we are going to see that same flow gets distorted. What it going to have is that when the flow passes over it, it tries to expand. Expand means this Mach number becomes 1. At one particular point, when Mach number becomes 1, another features that drops in, which is the formation of shock waves. So, information of the shock wave or theory of shock wave we will discuss later, but at this stage the physics behind the flow past an airfoil, it will says that there will be a shock wave formation on the surface of the body, and this because of this shock wave the Mach number becomes higher, because flow becomes supersonic when it passing over this airfoil surface, and flow behind this becomes subsonic, and here also subsonic. Now, this particular flow is characterized as transonic flow. Now, if you keep on increasing this Mach number, so what is happening? This shock wave propagates towards the free stream. That means, at that free stream on the surface. So, and this and it keeps on moving. At one particular point, the flow becomes sonic, and you will find the shock wave, instead of on the surface, it will try to relocate itself as a at some distance, which is called as a standoff distance, and this particular shock we call this as a bow shock. And when you see the bow shock, we have the characteristics of this bow shock is such that the flow behind this, flow before this is supersonic, and flow after this is subsonic. So, we will encounter a very drastic change in the Mach number, that is Mach number becomes less than 1, and then further downstream the flow expands because it passes through a coarse surface. Now, moving further, we are looking at another situation where we are increasing this Mach number, free stream Mach number, which is more than 1.2. In fact, in the range of 0.8 to 1.2, entire flow is characterized as transonic flow. Now, when the flow Mach number again increases more than 1.2, that is free stream, and when we look at this free stream flow which is passing over a wedge, this is nothing but a wedge. So, why we say wedge? Because normally the aerodynamic configurations which are used in the supersonic flow are wedge shapes or it is a sharp objects, and this because of the supersonic nature of the flow, whatever we see this shock wave which is standing here, it becomes attached on this edge of this wedge, and this because of this shock wave the flow will have two different streamlines. One is before this shock, another is after this shock. The streamline passing through this shock before in the free stream area, they are parallel to the free stream flow. Now, when you see the streamlines after this shock, they are parallel to this wedge surface. So, this is what we call as a supersonic flow. Now, if the flow Mach number or free stream Mach number increases further, which is more than 5, these shock waves gets squeezed in the very thin region of the wave, which means you do not feel any streamlines after this shock. Although the Mach number is again supersonic on the surface, but you will find you do not find any streamlines. So, effective shape of the body, which was the thickness of this wedge, now becomes effective size becomes higher, which means this entire streamline gets squeezed onto the surface, and we call this, and that means the shock wave is almost sitting on the surface. We call this as a thin shock layer. So, the effect of this thin shock layer is to increase the effective size of the wedge. So, as if there is a strong region of high temperature and pressure which gets induced by this by the flow, free stream flow, and such a flow is characterized as hypersonic flow. So, this is the entire information of the flow regime. Now, if you go to one by one, which I have elaborated here. So, what we see is that we look for the arbitrary point in the flow field, where you denote this pressure, temperature and density and velocity, and this is nothing but at some point in the downstream of the flow, it can be on the surface, it can be on the any streamline which is downstream of the flow, and this downstream flow gets affected because of the nature of what nature of the free stream flow is we look at. So, for this we classify the two Mach numbers. One is the free stream Mach number m infinity, which is associated with the free stream flow. Other is the local Mach number, which is encountered on this body surface. Okay. So, obviously, Mach number becomes a non-dimensional parameter that talks about the ratio of velocity to the speed of sound. Now, let us try to see that effective characteristics for a subsonic flow when free stream Mach number is less than 0.8. So, in this case the local Mach number is less than unity everywhere in the flow field, and the flow is characterized by streamlines with continuously varying properties on this airfoil. Okay. Now, when you move on to translink flow in the range of 0.8 to 1.2, that means this particular domain. So, what we see that in the initial state we have a shock wave on the surface, and the shock wave moves downstream, moves upstreams, and it becomes a bow shock that sits at the leading edge of the airfoil, and that is the distance which is called as standoff distance, which is defined by this term. And this particular zone is a mixed region of subsonic supersonic flow, which means this side you have supersonic, this here subsonic, again we have supersonic flow. So, this is called as a transonic flow. That means, flow field involving subsonic and supersonic nature becomes a transonic flow. Then moving for supersonic flow, which is characterized as free stream Mach number higher than 1, and of course, to be more precise, it has to be more than 1.2. And when you have this, we will have a streamlines which is parallel to the free stream, this is before this shock, and here the shock wave is called as a oblique shock, and after this shock the streamlines that comes, it takes the it becomes parallel to the surface of this wedge, that is after it crosses the oblique shock. Now, when you move for that means the supersonic uniform free stream is not forewarned by the presence of the body until the shock wave is encountered. So, this is the characteristics of supersonic flow. And for hypersonic flow, when the Mach number is higher than 5, this oblique shock becomes thinner and thinner and it sits on the surface. So, we will feel that the flow properties changes drastically or exponentially within this thin shock layer close to the surface. So, this particular flow field is characterized as high temperature chemically reacting flow which prevails on this surface. This is called as high temperature chemically reacting flow. So, all these flow regimes whatever we have discussed so far, these are compressible domain. The other extreme which is called as what happens, we say that subsonic flow is felt when the Mach number is less than 0.8, but what happens much before that? Is there any really compressible effect comes into picture or not? To do that, let us see this particular information which is we call this as incompressible flow. As I mentioned, if it is a liquid, it is a flow is completely incompressible, but the gases behave dual behavior with incompressible nature and compressible nature. So, under what circumstances the gases behaves incompressible nature and under what circumstances gases behave compressible natures, that is detected by Mach, again by the Mach number. So, to make a more precise information, what we say, if you define the Mach number as V by A, so Mach number becomes 0, that means role of Mach number becomes 0 means V infinity is 0, which means body is not travelling. But if you look at the situation when by equation, from this equation, when A infinity goes to the very high value, so the Mach number tends to 0, which other way means that isentropic compressibility tends to 0. So, based on the speed of sound and relation between isentropic compressibility, this will only true, which means that density variation is negligible. So, that information says that when there is effect of speed of sound, there is no effect of speed of sound, flow is completely incompressible. Other extreme is that if you talk about the very extreme situation of hypersonic flow, that means we say that hypersonic flow is encountered when Mach number reaches 5. What happens if what happens when the flow Mach number becomes 20 or 30? Under that circumstances, that is called as extreme situation of hypersonic flow. So, there the continuous hypothesis is violated, where mean distance of atom and molecules between collision becomes the order of magnitude, it becomes the characteristics dimension of the flow, and such a flows are called as low density and rarefied flow. Under extreme situation of non-continuum flow, mean free path becomes much larger than the characteristics length. So, as I mentioned in our previous informations, we say that parameter is detected by a number called as Bunsen number, and that is defined as the ratio of molecular mean free path to the characteristics dimensions, that is lambda by L. So, when this Knudsen number is much less than 0.1, we say it is a continuum flow and becomes 0.01 to 1, it becomes a slip flow, and when it becomes more than 1, it is a free molecular flow. That means as if there is no molecules present during that time, which means this particular situation we call as a non-continuum flow. So, this is all about the flow regimes starting from incompressible to the extreme hypersonic flow, and that is the range of compressible flow domain. So, our attention from the subsequent class onwards will be mainly the theory behind this compressible flow mainly for supersonic flow, and to some extent when the flow approaches to hypersonic in nature. So, before I conclude, let me try to give some basic framework or understanding through a numerical problem with a basic definition of incompressible flow and compressible flow nature. So, let us see, we say that density variations are quite significant in a compressible flow, but to what extent? Now, if you want to have some precise information, let us try to understand that in a given flow field, how these density variations are calculated, based on which the judgments are made whether the domain is compressible or not. Here we have given similar concept in the form of a problem, which says that a low speed flow over an airplane wing with standard sea level conditions, the free stream velocity ahead of this wing is 45 meter per second. Flow accelerates over the wing to a maximum velocity of 70 meter per second at some point on the wing. What is the percentage change of pressure between this point and free stream, assuming the incompressible flow? What is the density change between this point and free stream, assuming the flow to be compressible? So, what we look at? We talk about the cross section of a airplane wing, which happens to be an airfoil. So, you draw an airfoil and we see that some stream is approaching with its initial velocity v1 is 45 meter per second. And when the flow passes over this airfoil at some point B, so this is the free stream, and at some point the flow the speed becomes 70 meter per second. So, we say this is region 1 and this is region 2. So, the first part of the problem you can solve in this manner, that since the flow is incompressible, that means rho is constant. So, once the rho is in constant, so you can apply Bernoulli's equation to get fundamental Bernoulli equation, which you encounter in the conventional fluid mechanics course for an incompressible flow. We can write as P1 plus half rho 1 V1 square is equal to P2 plus half rho 2 V2 square. So, this will give you the basic information, that is P1 minus P2 is equal to half rho V2 square minus V1 square. So, here it is a sea level condition. So, for which we can say density may be 1.2 kg per meter cube, pressure is 101,325 Pascal, temperature may be 300 maybe let us say 288 Kelvin. So, this is the basic information that we will get from the sea level data. So, from these equations we know rho, we have V2 and V1. So, we can find out P1 minus P2 as 1725 kilopascal. So, this we get by putting the information of V1, V2 and rho. But what we require is that pressure change between this point and free stream. That means P1 minus P2 by P1, that information we require. So, this becomes 1725 divided by P1, already we have 101325. So, this number happens to be 0.017. So, what we see is that pressure change is almost insignificant. That means, whatever pressure is felt by the free stream, same pressure is also experienced at the surface, insignificant. Since there is pressure change is insignificant, so which means this also implies your d rho is also small. So, which means justification of incompressible is justification of flow to be incompressible is also valid, because we have already assumed density to be constant. Now, this is for the part A problem. Now, for the part B problems, we expect that assuming that flow to be compressible. So, we are going to see if it is a compressible flow problem, then obviously we cannot use in Bernoulli's equations. So, we have to revisit the energy equation that we have studied from the one dimensional framework. So, that equation we can write H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. So, H becomes Cp times T, because it is air medium, plus V1 square by 2 is equal to Cp T2 plus V2 square by 2. So, from this equation, what is your expectation that we should get? What is T2? That is equal to T1 plus V1 square minus V2 square by 2. Now, T1 is given as 288 Kelvin, V1 and V2 information are here. So, this will give you T2 becomes 286.5 Kelvin. So, you can recall that your T1 is 288, T2 is 286, hardly there is a drop in temperature. And but what we require is that you require density change. So, you recall this isentropic relation between temperature and density, that is rho 2 by rho 1 is equal to T2 by T1 to the power 1 by gamma minus 1. So, since it is air, you have gamma is equal to 1.4, and we can get rho 2 by rho 1 by putting the information of T2 and T1 is 0.98, which means rho 2 is equal to 1.17 kg per meter cube. So, how much change happens? So, from 1.2 kg per meter cube it changes to 1.17 kg per meter cube. So, if you say rho 2 minus rho 1 by rho 1 ratio, so this turns out to be 0.02, and since it is d rho by rho is much less than 2%, which means the flow is still incompressible. So, that means the justification, our assumption of incompressible nature is not relevant for this kind of situations. So, this is how you have to make judgment that if there is a significant drop in the flow velocity or these things, then only we can say the flow falls in the compressible domain. However, for this particular problem, the entire flow field is incompressible nature. So, whether you use Bernoulli's equations or energy equation for compressible flow, both bear the same results. So, with this I conclude. Thank you for your attention.